Hi, Assalamualaikum. In this presentation, we will introduce the main mathematical tools used in quantum mechanics. In quantum mechanics, we need mathematical machinery to describe physical system accurately. One of the main equations in this theory is Schrödinger equation, and it has the structure of a linear equation. Because of this, quantum mechanics use linear operator and wave function. This wave function belongs to a mathematical space called Hilbert space. Hilbert space is essential because it provides the correct framework to describe quantum state and their properties.
Linear vector space, in quantum mechanics is also known as Hilbert space, is the abstract playground where all possible states of a quantum system live. It consists of two sets of elements, which are a set of scalars and a set of vectors, and two algebraic rules, which are a rule for vector addition and a rule for scalar multiplication. Now we will moving on to the addition rule for the set of vectors. The addition rules has the properties and structures of an abelian group. For the first point, if psi and phi are vectors or elements in a space, their sum, psi and phi, is also a vector of the same space. For the point for the commutativity, when a psi is added to a phi, it will equal to a phi when added to a psi. For the third point, which is the associativity, when a psi and phi is added in a bracket plus with another vectors, it will also equals to a psi added to a phi and other vectors in a bracket. For the fourth point, existence of neutral or zero vector. For each vector psi, there must be a corresponding zero vector such that when it is added to any of vectors which is psi or a phi, it will equal to the vectors itself. For the last point of addition rule, existence of symmetric or inverse vector. Each vector psi must have their own symmetric vector, such as negative psi, so that in the calculation, when psi is added to the negative psi, it will equal to 0. Moving on to the multiplication rule for a set of scalars. The multiplication of vectors by scalars, either real or imaginary numbers, has these properties, which are product of a scalar and a vector will produce a vector. If a psi and phi are two vectors in a space, any linear combination a psi plus b phi is also a vector in the space where a and b being scalars. For the distributivity with respect to addition, I will give you an example which when a is a multiple with psi plus phi in a bracket, it will equal to a psi plus b phi. For the associativity with respect to multiplication of scalars, I will give you an example. Like when a is multiple with b phi, it will also equals to ab in bracket a multiple with phi. For each element psi, there must be a corresponding unitary scalar and a zero scalar such that when psi is equal to psi in a modulus, it will equal to psi, and when the psi is multiple with a 0, it will equal to 0. Now moving on to the Hilbert space that is notated by H, have a set of vectors and a set of scalars that satisfy 4 of the following properties, which is the first one, and Hilbert space is the linear space. The second one, Hilbert space has a defined scalar product that is strictly positive, where the scalar product of psi with phi is equal to the complex conjugate of the scalar product of phi with the third one. The scalar product of phi with psi is linear with respect to the second factor if psi is equal to a psi 1 plus b psi 2. In the equation, in the bracket, phi a psi 1 plus b psi 2 is equal to a in the bracket phi psi 1 plus b in the bracket phi psi 2, and antilinear with respect to the first factor if phi is equal to a phi 1 plus b phi 2, which in the bracket a phi 1 plus b phi 2 psi is equal to a complex conjugate to the phi 1 psi plus b complex conjugate to the phi 2 psi. And for the fourth properties, which are the scalar product of a vector psi with itself is a positive real number. When psi is multiple by psi, it will equals to a real number, not an imaginary number, where the equality holds only for psi equals to 0.
So first, what is a wave function? A wave function is a mathematical function used to describe the quantum state of a physical system. It is usually written as psi of x and t or psi of r and t. Although the wave function itself has no direct physical meaning, it contains all the information needed to describe the system. About the probability interpretation, the physical meaning of the wave function comes from its square modulus. According to Born interpretation, the modulus square of the wave function represents probability density. This equation is written as the integral of the modulus square of psi of r and t over all space must equals to 1. This condition ensures that the particle must be found somewhere in space. The dimension of a vector space is defined as the maximum number of linearly independent vector in that space. Linearly independent vector are vectors that cannot be expressed as linear combination of other vectors. In quantum mechanics, Hilbert space are usually infinite dimensional. The sum from I equals 1 to n of a subs I times cat I equals to 0. This equation defines that it was a linear independence. If this equation is satisfied only when all coefficients are 0, then the vectors are linearly independent. So next, basis of a vector space. A basis is a set of linearly independent vector that spans the entire vector space. This equation is read as psi cat equals the sum from I equals 1 to n of a subs I times cat I. This means any vector in the space can be written as a linear combination of a basis vector. Next, for a square integrable function, in quantum mechanics, wave function act as a vector in a Hilbert space because they behave like a vector. We can define a scalar product between two wave functions using an integral. The scalar product of psi and phi equals the integral of psi star of x times phi of x dx. At here, the star represents the complex conjugate of the wave function. For the scalar product to exist, the value of the integral must be finite. This is why not all functions are allowed in quantum mechanics. For a square integrability condition, we need to make sure that a wave function can represent a physical system. For this reason, the wave function must satisfy a mathematical condition called square integrability. The integral of the modulus square of psi of x dx is less than infinity. This means the total probability is finite. Only wave functions that satisfy this condition are physically meaningful in quantum mechanics. Lastly, why it is important in quantum mechanics because the set of all square integrable wave functions forms a Hilbert space with infinite dimension. This structure allows quantum system to be described accurately. It is one of the fundamental mathematical tools in quantum mechanics.
To simplify the mathematical description of quantum mechanics, Paul Adrian Dirac introduced a very powerful notation known as Dirac notation. The main purpose of this notation is to free quantum state vector from coordinate representation, making the formalism easier and clearer to use. In this notation, a quantum state is written as a cat, which belongs to the Hilbert space. Every cat has a corresponding bra, which belongs to dual space. When a bra and a cat are combined, we obtain a bra cat, which represent the scalar or inner product between two quantum states. When a cat or bra is multiplied by a complex number, we also get a cat or bra. Next, I will present about properties of bra, cat, bra cat. First, every cat has a corresponding bra. A cat represents the state of quantum system, while the corresponding bra is dual of the cat. The bra is obtained from the cat by taking the complex conjugate transpose. Second, properties of scalar product. The scalar product is a complex number that measures the overlap or similarity between two quantum states. The order of bra and cat is important because interchanging them gives the complex conjugate of the original scalar product. Next, the norm of a state is always real and positive and also represent the length or magnitude of the state vector. A quantum state is said to be normalized when norm is equal to 1. Normalization ensures that the total probability of all possible outcomes is equal to 1. Next, the Schwarz inequality states that the square of a magnitude of the scalar product of two states is less than or equal to the product of their norms. This inequality limits how large the overlap between two quantum states can be. Next, the triangle inequality states that the norm of the sum of two quantum states is less than or equal to the sum of their individual norms. This property shows that combining two states cannot produce a state with a length greater than the sum of their length. Next is orthogonal state. Two quantum states are said to be orthogonal if their scalar product is equal to 0. Orthogonal states have no overlap and represent completely independent physical states. Last one is orthonormal state. A set of quantum states is called orthonormal if each state is normalized and every pair of different states is orthogonal. In conclusion, quantum mechanics cannot be understood without mathematics. The wave function tells everything about the state of a particle. To represent this wave function, we use vector space and Hilbert space. This space allows to treat quantum state as mathematical vector. The concept of basis and dimension helps to know how many independent states are needed to describe a system. Finally, Dirac notation gives a simple and powerful way to write quantum state and perform calculation. Overall, all these mathematical tools work together to help describe, analyze, and predict the behavior of particles in quantum world.